rapid birth of stars is fueled by an abundance of interstellar gas and dust, which collapse under gravity to form stellar nurseries. However, the conditions within the Cigar galaxy are far from tranquil. The immense energy released during star formation creates powerful stellar winds and supernova explosions that disrupt the surrounding interstellar medium. This turbulent environment is a hallmark of starburst activity. One of the most striking features of the Cigar Nebula is the vast, fiery outflow of gas and dust streaming outward from its central regions. This phenomenon, known as a galactic superwind, is driven by the collective energy of thousands of massive, young stars and supernovae. The superwind is composed of ionized hydrogen, oxygen, and other elements, which are ejected into the intergalactic medium at speeds exceeding 1,000 kilometers per second. These outflows are not only visually spectacular but also play a crucial role in the evolution of the galaxy. By expelling gas and dust, the superwind limits future star formation within the system and enriches the surrounding intergalactic environment with heavy elements. The starlight forge has a highly irregular and distorted shape, making it an atypical member of the galactic family. Its elongated structure and chaotic morphology are likely the result of gravitational interactions with its neighboring galaxy, M81. The two galaxies are part of the M81 group, a small collection of galaxies bound together by gravity. Over the past few hundred million years, the gravitational forces between M82 and M81 have triggered tidal interactions that have stirred up the gas and stars within both systems. These interactions are thought to have initiated the intense starburst activity within the Torch galaxy. A distinctive feature of the smoldering spiral is its central region, where a supermassive black hole resides. This black hole, millions of times the mass of the Sun, influences the dynamics of the galaxy's core. Observations in multiple wavelengths, including X-rays, radio, and infrared, have revealed the presence of an active galactic nucleus, AGN, at the heart of the galaxy. The AGN emits high-energy radiation, which interacts with the surrounding matter and contributes to the overall energy output of the system. This interaction is another factor driving the extreme conditions within the Ember galaxy. In addition to its superwind and starburst activity, the glowing inferno is notable for its complex magnetic field. Studies using polarized radio observations have revealed large-scale magnetic structures extending outward from the galaxy's central regions. These magnetic fields are believed to play a role in shaping the galactic superwind and influencing the distribution of cosmic rays. Understanding the interplay between magnetic fields and galactic dynamics is a key area of research in modern astrophysics, and the Flame Nebula provides an excellent laboratory for studying these phenomena. The radiant rift is also a prolific source of cosmic rays and high-energy particles. Observations in gamma rays and X-rays have shown that the galaxy's core is teeming with energetic phenomena. These emissions are associated with the intense star formation and supernova activity occurring within the system. Cosmic rays generated in the galaxy's core propagate outward, interacting with the interstellar medium and contributing to the overall energy budget of the surrounding space. One of the most significant discoveries about the bright beacon came from observations in the infrared spectrum. Using advanced space-based telescopes such as the Spitzer Space Telescope and the Hubble Space Telescope, astronomers have mapped the distribution of dust and molecular gas within the galaxy. These studies have revealed a complex network of filaments and clumps, where star formation is occurring at an extraordinary rate. Infrared observations have also provided insights into the temperature, composition, and dynamics of the interstellar medium, shedding light on the processes driving the galaxy's starburst activity. The starfire expanse is not just a spectacle of astrophysical phenomena but also a key player in the cosmic ecosystem. The materials ejected in its superwind, including heavy elements like carbon, oxygen, and iron, enrich the intergalactic medium and contribute to the chemical evolution of the universe. These elements are the building blocks of planets, life, and other galaxies, making the galaxy's activity a crucial part of the cosmic cycle. In recent years, the beacon of creation has been the focus of numerous studies using advanced observatories and instruments. Telescopes like the Chandra X-ray Observatory, the Very Large Array, and the James Webb Space Telescope have provided high-resolution data across multiple wavelengths, allowing researchers to study the galaxy in unprecedented detail. These observations have not only deepened our understanding of the galaxy itself but also provided valuable insights into the broader processes of galaxy evolution, star formation, and cosmic feedback. Despite its relative proximity to Earth, the Cigar galaxy continues to hold many mysteries. Questions remain about the exact mechanisms driving its starburst activity, the long-term effects of its interactions with M81, and the fate of its expelled gas and dust. As observational technology continues to advance, astronomers are likely to uncover even more secrets about this dynamic and enigmatic system. The Torch Nebula serves as a vivid reminder of the dynamic and interconnected nature of the universe. Its intense activity, dramatic outflows, and complex interactions with its environment exemplify the forces that shape galaxies and influence their evolution over cosmic timescales. For scientists and enthusiasts alike, the Stoga spiral remains a source of wonder and inspiration, a celestial beacon illuminating the complexities of the cosmos. The Cigar galaxy, or Messier 82, remains a prime focus of astronomical studies, not only for its unique features, but also for the critical role it plays in unraveling the mysteries of galaxy evolution. This starburst system is a living laboratory, showcasing the dynamic interplay between gravity, star formation, and cosmic feedback on an extraordinary scale. One of the lesser discussed, but equally fascinating aspects of the fiery veil is the role of supernovae in shaping its environment. Supernova explosions, the catastrophic deaths of massive stars, release immense amounts of energy and enrich the surrounding interstellar medium with heavy elements. These events also drive shockwaves through the galaxy, compressing gas clouds and triggering further waves of star formation. In the case of M82, the supernova rate is significantly higher than that of typical galaxies, with a new supernova occurring approximately every 20 to 30 years. This elevated rate underscores the intensity of the starburst activity and its profound impact on the galaxy's overall structure and evolution. The firebrand nebula's proximity to its neighbor, the Grand Spiral Galaxy, M81, has also resulted in the transfer of material between the two systems. This gravitational interplay has created tidal streams of gas and stars that stretch across the intergalactic space between them. These streams, rich in hydrogen and other elements, act as cosmic highways for matter, fueling further activity within both galaxies. The interaction also serves as a natural experiment in galaxy dynamics, allowing researchers to study how gravitational forces influence galactic evolution over millions of years. Beyond the optical and infrared observations, the bright blaze has been extensively studied in radio wavelengths, revealing a wealth of information about its magnetic fields, cosmic rays, and neutral hydrogen distribution. Radio telescopes have detected large-scale outflows of neutral hydrogen gas, which are expelled from the galaxy's disk by the powerful galactic superwind. This process, known as galactic outflow, is a critical mechanism in regulating star formation. By expelling gas, the galaxy limits the amount of material available for future star formation, thereby moderating its growth and evolution. Interestingly, the flame rift has been found to host a unique population of massive molecular clouds, regions rich in molecular hydrogen and other complex molecules. These clouds, some of the largest observed in any galaxy, serve as stellar nurseries where the next generation of stars is born. The conditions within these clouds are extreme, with high temperatures, turbulent motions, and intense radiation fields. Studying these regions provides invaluable insights into the processes that govern star formation under such harsh conditions. The dusty inferno also exhibits an unusual pattern of chemical enrichment. Observations of the outflows have shown that the ejected material is not evenly mixed, but rather stratified, with lighter elements being pushed out further than heavier ones. This stratification is a direct result of the physics of the galactic superwind, where lighter ions are more easily accelerated by the energy of supernovae and young stars. This phenomenon provides a unique opportunity to study the chemical evolution of galaxies and the dispersal of elements into the intergalactic medium. Another key area of study in the glimmering hearth is the interaction between its central supermassive black hole and the surrounding matter. Observations in X-rays and gamma rays hints of high-energy phenomena occurring in the vicinity of the black hole. These include the acceleration of particles to near-light speeds and the generation of relativistic jets, which can extend thousands of light-years into space. These jets, although less prominent than those in some active galaxies, still contribute to the overall energy dynamics of the system and influence the behavior of the surrounding gas and dust. In the far-infrared spectrum, the starlight blaze reveals the presence of warm dust heated by intense radiation from young, massive stars. This warm dust emits light at wavelengths invisible to the human eye but detectable by specialized instruments. The distribution of this dust, along with its temperature and composition, provides clues about the starburst activity and the conditions within the galaxy. Infrared studies have also identified regions of intense star formation hidden behind thick clouds of dust, which would otherwise remain obscured in visible light. The halo flame, the extended halo of gas and stars surrounding M82, is another area of intense scientific interest. This halo, composed of both old stars and newly ejected material, is a direct result of the galaxy's turbulent history. The halo contains streams of stars pulled from the galaxy by tidal interactions, as well as gas and dust expelled by the galactic superwind. Studying this halo offers a glimpse into the long-term effects of the starburst activity and the galaxy's interactions with its environment. Finally, the Cigar cluster, the system's broader galactic neighborhood, provides context for understanding its evolution. The M81 group, which includes M82, M81, and several smaller galaxies, is a microcosm of cosmic interactions. The gravitational interplay within this group has led to the formation of tidal bridges, gas streams, and other structures that illustrate the interconnected nature of the universe. By studying the Cigar galaxy in the context of its galactic group, astronomers can better understand the processes that shape galaxies and drive their evolution over billions of years. The Cigar galaxy remains a shining example of the universe's complexity and beauty. Its dynamic nature, rich structure, and profound impact on its surroundings make it a cornerstone of modern astrophysical research. As telescopes and observational techniques continue to improve, the secrets of this remarkable galaxy will undoubtedly yield even deeper insights into the fundamental workings of the cosmos. The dynamic evolution of the Cigar galaxy, or Messier 82, continues to challenge and expand our understanding of galactic processes. Its uniqueness lies not only in its dramatic starburst activity, but also in the interplay of forces that define its structure, behavior, and influence on the surrounding universe. Researchers have identified several emerging areas of interest that further highlight the intricacies of this galactic marvel. The superwind phenomenon in the Torch Nebula is a crucial example of feedback in galaxy evolution, a process where energy and matter expelled from the galaxy interact with its surroundings. This feedback regulates the star formation cycle by dispersing gas and dust, while also enriching the intergalactic medium. Recent observations suggest that the superwind in M82 extends far beyond the central regions, reaching distances of over 10,000 light-years. These winds are now known to influence nearby galaxies, including M81, by injecting energy and redistributing materials into their shared environment. Researchers have also discovered that these winds are not uniform. Instead, they form intricate, layered structures with varying densities, temperatures, and velocities. The interactions between different layers of the outflow generate shock waves and turbulence, which further modify the surrounding medium. By studying these outflows in detail, scientists are uncovering the complex mechanisms that govern galactic feedback and its role in shaping both individual galaxies and larger-scale cosmic structures. The ongoing starburst activity in the starlight furnace occurs under conditions far more extreme than those in typical galaxies. The central regions of the galaxy, where the most intense star formation takes place, are characterized by extraordinarily high pressures, temperatures, and radiation levels. These conditions create a unique environment for the birth of stars, leading to the formation of massive stellar clusters with populations of hot, short-lived stars. One of the most intriguing aspects of this process is the role of turbulence in compressing gas clouds to trigger star formation. The chaotic flows of gas and dust within the galaxy create regions of high density where gravitational collapse occurs. However, this turbulence also acts as a double-edged sword, dispersing some gas clouds before they can form stars. Understanding this balance between compression and dispersal is a key challenge in astrophysics, and the Ember spiral provides an ideal testbed for exploring these dynamics. Magnetic fields play an often overlooked but vital role in the evolution of galaxies, and the fiery haven is no exception. Observations using radio telescopes have revealed that M82's magnetic fields are closely aligned with the structures of its galactic outflows. These fields act as channels, guiding the movement of charged particles and shaping the morphology of the superwind. Additionally, magnetic fields help to regulate the flow of cosmic rays, which are high-energy particles produced by supernovae and other energetic processes within the galaxy. The interplay between magnetic fields and starburst activity is an active area of research. Scientists are investigating how these fields influence the distribution of gas and dust, as well as their role in supporting or suppressing star formation. By mapping the magnetic field structures in detail, researchers hope to uncover the underlying physics that governs these interactions. The study of the Blaze Nebula has benefited immensely from advancements in multi-wavelength astronomy. Observing the galaxy across the electromagnetic spectrum, ranging from radio waves to gamma rays, has revealed a wealth of information that would be inaccessible through a single wavelength alone. For example, X-ray observations have uncovered the presence of ultraluminous X-ray sources, ULXs, within the galaxy, which are thought to be associated with black holes or neutron stars accreting matter at extraordinary rates. Infrared and sub-millimeter observations have provided detailed maps of the galaxy's dust content, showing how it is distributed and heated by star formation. Meanwhile, gamma-ray studies have shed light on the energetic processes occurring in the galaxy's core, including the production of high-energy particles and their interactions with the surrounding medium. This multi-wavelength approach has transformed our understanding of the galaxy, highlighting the importance of combining data from different parts of the spectrum to gain a comprehensive view of complex astrophysical systems. Beyond its immediate environment, the Starfire Rift has a far-reaching influence on the cosmic web of galaxies. The materials ejected in its superwind, particularly heavy elements such as carbon, oxygen, and iron, contribute to the chemical enrichment of the intergalactic medium. These elements are essential for the formation of planets, complex molecules, and eventually, life itself. In this way, the galaxy's activity plays a crucial role in the broader evolution of the universe, seeding the cosmos with the building blocks of matter. Moreover, the interactions between M82 and its galactic neighbors provide insights into the processes that drive galaxy clustering and group dynamics. The tidal forces exerted by M81 and other members of the M81 group have not only shaped the structure of the radiant furnace but also triggered its intense starburst activity. These interactions serve as a microcosm of the larger-scale processes that govern the formation and evolution of galaxy clusters. As technology continues to advance, the bright inferno remains a focal point for cutting-edge astronomical research. Next-generation telescopes such as the James Webb Space Telescope, JWST, and the Extremely Large Telescope, ELT, promise to deliver even more detailed observations of this enigmatic galaxy. These instruments will allow scientists to probe the smallest scales of star formation, map the distribution of elements in unprecedented detail, and explore the galaxy's interactions with its environment at higher resolutions. Additionally, the development of advanced computational models is enabling researchers to simulate the evolution of the Flame Nebula and other starburst galaxies. simulations, informed by observational data, provide a powerful tool for testing theories of galaxy formation and evolution. By comparing the results of these models with real-world observations, scientists can refine their understanding of the physical processes at work. In many ways, the Cigar galaxy serves as a cosmic beacon, illuminating the forces that shape galaxies and drive their evolution. Its flows, intense starburst activity, and complex interactions with its surroundings offer a vivid portrait of the dynamic universe we inhabit. As we continue to study this remarkable system, it reminds us of the intricate and interconnected nature of the cosmos, where every galaxy is both a product of its environment and a contributor to the greater cosmic tapestry. The discoveries yet to be made in the Stoga Nebula promise to deepen our appreciation of the universe's beauty and complexity, inspiring future generations of scientists and explorers to unravel its secrets. The Cigar galaxy, with its chaotic and vibrant processes, is also a remarkable laboratory for studying how starburst activity affects the long-term evolution of a galaxy. Its rapid production of new stars comes at a cost, as the massive stellar feedback is gradually depleting the supply of gas required for future star formation. Observations indicate that much of the gas expelled in the superwind escapes the gravitational pull of the galaxy, venturing into the surrounding intergalactic medium. This process not only transforms the internal dynamics of the galaxy, but also has a significant impact on its future trajectory as a star-forming system. The central regions of the galaxy, where the starburst activity is concentrated, reveal a wealth of details about the processes occurring in such environments. These regions are dominated by clusters of young, massive stars, which emit intense ultraviolet radiation and stellar winds. The radiation pressure from these stars, combined with the mechanical energy from stellar winds, creates powerful bubbles of ionized gas that expand outward, merging into the larger-scale galactic superwind. This feedback process is critical for regulating the density and temperature of the interstellar medium, influencing where and when new stars can form. One of the remarkable aspects of this galaxy is the intricate interaction between gravity, turbulence, and radiation in shaping its structure. Gravitational interactions with M81 have created tidal streams and disrupted the distribution of gas and stars, resulting in a highly irregular morphology. Meanwhile, turbulence generated by supernova explosions and stellar winds acts on smaller scales, compressing gas in some regions while dispersing it in others. These competing forces create a dynamic equilibrium that governs the overall behavior of the galaxy. The chemical enrichment observed in the expelled gas and dust provides a unique insight into the life cycle of matter in the universe. The super wind carries with it the byproducts of nuclear fusion within stars, including heavy elements such as carbon, nitrogen, and oxygen. These elements, created in the cores of stars or during supernova explosions, are essential for the formation of planets and organic molecules. By expelling these materials into the intergalactic medium, the galaxy contributes to the ongoing chemical evolution of the cosmos, ensuring that future generations of stars and planets are enriched with the building blocks necessary for complexity in life. The halo surrounding the galaxy is another fascinating feature, serving as a reservoir of both old stars and newly ejected material. This halo extends far beyond the visible disk of the galaxy, blending into the larger environment of the M81 group. Studies of this halo reveal that it contains a mix of stellar populations, including stars stripped from the galaxy by tidal interactions and those formed in situ from expelled gas. The interplay between the halo and the galaxy itself provides valuable clues about the processes that shape the outer regions of galaxies and their connections to the larger cosmic web. The role of cosmic rays in the dynamics of the galaxy is an area of active research. These high-energy particles, generated by supernova explosions and other energetic events, interact with the magnetic fields and gas in the galaxy, influencing the behavior of the superwind. Observations suggest that cosmic rays may help to accelerate the outflow of gas, providing additional energy to drive the material into intergalactic space. Understanding the contribution of cosmic rays to galactic feedback is an important step toward building a complete picture of how galaxies evolve over time. The interaction between the central supermassive black hole and its surrounding environment is another key aspect of the galaxy's dynamics. While the black hole in the Cigar galaxy is not as active as those in some other galaxies, it still plays a significant role in shaping the core of the system. Observations in X-rays and other wavelengths indicate that the accretion of material onto the black hole produces energetic outflows and radiation, which can influence the behavior of gas and stars in the central regions. These processes are part of a complex feedback loop that regulates the growth of the black hole and the starburst activity in the galaxy. The study of this galaxy has also highlighted the importance of large-scale structures in the universe. The interactions between the Cigar galaxy and its neighbors, particularly M81, demonstrate how galaxies within a group can influence each other over billions of years. These interactions are responsible for triggering the starburst activity in the Cigar galaxy, as gravitational forces compress its gas and disrupt its equilibrium. By studying these processes in detail, astronomers can gain a better understanding of how galaxies evolve within the context of their larger cosmic environments. Advancements in observational technology have allowed scientists to probe the galaxy in unprecedented detail, revealing structures and processes that were previously invisible. Instruments like the Atacama Large Millimeter / Submillimeter Array (ALMA) have provided high-resolution maps of the galaxy's molecular gas, showing how it flows and accumulates in regions of intense star formation. These observations have revealed a surprising level of complexity, with gas streams, filaments, and clumps interacting in ways that challenge existing models of galaxy dynamics. The ongoing study of the Cigar galaxy is not only revealing new insights about this specific system but also providing a deeper understanding of the fundamental processes that govern galaxies throughout the universe. By examining the intricate interplay of forces within this starburst galaxy, scientists are uncovering the mechanisms that drive star formation, regulate galactic feedback, and shape the evolution of galaxies over cosmic timescales. The discoveries made in this system are helping to build a more complete picture of the universe, one that highlights the interconnected nature of all its components. The Cigar galaxy continues to mesmerize astronomers and enthusiasts alike, standing as a beacon of cosmic drama and complexity. Its very existence challenges preconceived notions about how galaxies evolve and thrive under the universe's most chaotic conditions. Every detail of its fiery heart and windswept edges invites a deeper exploration, pulling us into the intricate ballet of gravity, turbulence, and creation. The galaxy's starburst activity is not just an isolated marvel, it is a cosmic performance on a grand scale. Imagine billions of stars igniting in rapid succession, their collective brilliance radiating outward, flooding the surrounding space with light, heat, and energy. The sheer scale of this activity is almost incomprehensible, a relentless wave of creation and destruction unfolding across tens of thousands of light years. This celestial furnace is not merely producing stars. It is forging the building blocks of future galaxies, solar systems, and potentially even life itself. Delving deeper into the superwind phenomenon, one can imagine the sight of colossal plumes of glowing gas and dust erupting from the galaxy's core, stretching far into the surrounding space. These outflows, driven by the energy of countless supernovae and stellar winds, are cosmic storms of unimaginable power. They carry with them not just the raw materials of stars, but also the fingerprints of the processes that created them. Heavy elements forged in the hearts of dying stars, now cast out into the universe to seed new generations of celestial wonders. As we peer closer at the galaxy's central regions, a hidden world of turbulence and brilliance emerges. Clouds of gas swirl in chaotic eddies, illuminated by the inlet radiation of young, massive stars. The interplay of light and shadow creates an ever-changing tapestry, where dense regions collapse under gravity to form new stars, only to be torn apart by the very forces they create. This cycle of creation and destruction is a testament to the dynamic nature of the cosmos, where nothing remains static, and everything is in a state of constant evolution. The galactic core itself is a cauldron of extremes, a region where the rules of physics are pushed to their limits. Here, the supermassive black hole exerts its influence, subtly shaping the behavior of gas and stars around it. While less active than the black holes in some other galaxies, this gravitational giant is architect, subtly orchestrating the flow of matter in its vicinity. High-energy jets and radiation from the black hole interact with the soul, adding yet another layer of complexity to this already intricate system. Evitable boundaries of the galaxy, the influence of the Cigar galaxy can be felt. The expelled material from its superwind does not simply vanish, it forms a vast halo of enriched gas and dust, a cosmic bridge connecting the galaxy to its neighbors and the wider universe. This halo, a faint but vital extension of the galaxy, is a reminder that no part of the cosmos exists in isolation. The materials ejected from the galaxy today may one day become the seeds of new stars and galaxies in a distant corner of the universe. The gravitational dance between the Cigar galaxy and its neighbor, M81, adds yet another layer of fascination. Their close encounters have left visible scars, tidal streams of stars and gas that weave between the two systems, evidence of their mutual influence over millions of years. These interactions are not destructive but transformative, fueling the intense starburst activity in the Cigar galaxy while reshaping the structure of both galaxies. It is a reminder that even in the vast emptiness of space, galaxies are connected, their fates intertwined in a grand cosmic narrative. In this ongoing story of fire and transformation, the Cigar galaxy stands as both a mystery and a promise. It is a snapshot of the universe in flux, a place where the boundaries between chaos and order blur, revealing the raw power and beauty of cosmic creation. As we gaze at this galactic masterpiece, we are reminded of our place in the universe, not as distant observers, but as participants in a story that began billions of years ago and continues to unfold around us. Every new observation of the torch spiral uncovers more layers of its complex nature, fueling the imagination and deepening our sense of wonder. What lies hidden in its swirling clouds of gas and dust? What secrets does its superwind carry into the vastness of space? And what role does it play in the grander scheme of cosmic evolution? These questions beckon us to explore further, to push the boundaries of what we know, and to embrace the unknown. The Cigar galaxy is not merely an object of study, it is an invitation to dream. It ignites our curiosity, reminding us that the universe is far larger, more dynamic, and more intricate than we can ever fully comprehend. Its glowing core, erupting outflows, and turbulent star nurseries call to us, urging us to look closer, think deeper, and imagine the possibilities that lie hidden among the stars. The story of this galaxy is far from over, and as we uncover more of its secrets, it continues to remind us that the universe is an endless wellspring of inspiration, waiting to be explored. The Cigar galaxy continues to captivate with its untamed energy, pushing the limits of what we know about the universe. Its very essence is a paradox, a place of both destruction and creation, where chaos gives rise to order and stars are born in fiery cataclysms. The closer we look, the more we realize how deeply interconnected this galaxy is with its environment and how its actions ripple across cosmic distances, influencing the very fabric of the universe. Its super wind, like a galactic exhalation, is a force of staggering power. Within it, streams of ionized gas and heated dust collide and interact, creating shock fronts that glow with an eerie, ethereal light. These winds don't just carry material, they carry stories. Every particle expelled tells the tale of its origin, forged in the core of a dying star, shaped by the explosive force of a supernova, and now cast into the intergalactic medium as part of a grand cosmic recycling process. What makes the superwind even more fascinating is its dual nature. On one hand, it strips the galaxy of the very resources it needs to sustain its starburst activity. On the other, it enriches the surrounding space, sowing the seeds for new structures, new stars, and even new galaxies far beyond M82's borders. As we venture deeper into the galaxy's core, we uncover a realm where gravity and radiation wage a constant battle. In this volatile region, massive molecular clouds twist and churn, their dense interiors acting as cradles for embryonic stars. These clouds are not passive, they are alive with activity, illuminated from within by the ultraviolet light of newly formed stars, which pierce through the surrounding dust like searchlights in a fog. The sheer density of this central region, with stars packed together thousands of times more tightly than in the Milky Way, creates a cauldron of activity that is both breathtaking and overwhelming. Amidst this intensity, we find traces of remarkable symmetry hidden within the chaos. Magnetic fields, like invisible threads, stretch across the galaxy, guiding the movement of charged particles and shaping the flow of its superwind. These magnetic fields act as architects, subtly influencing the galaxy's structure and behavior. They help channel cosmic rays, accelerate particles to near-light speeds, and regulate the distribution of gas, adding yet another layer of complexity to an already multifaceted system. Beyond the central chaos lies the extended halo, a region that, while less active, is no less intriguing. The diffuse envelope of gas, dust, and stars serves as both a record of the galaxy's history and a glimpse into its future. Within the halo are remnants of past interactions, tidal streams torn from the galaxy by gravitational encounters with M81, ancient stars scattered like breadcrumbs tracing the paths of these cosmic dances. This halo also acts as a bridge, connecting M82 to its surroundings and to the larger cosmic web of galaxies. The relationship between the Cigar galaxy and its neighbor, M81, continues to provide new insights into the nature of galactic interactions. Their gravitational embrace is a slow, cosmic waltz, one that has unfolded over millions of years and left both galaxies forever changed. For M82, these interactions have acted as a spark, igniting its starburst activity and reshaping its structure. For M81, they have led to the formation of intricate tidal streams and filaments, adding to the tapestry of their shared environment. This interplay is not merely a local phenomenon, it mirrors the behavior of galaxies on a larger scale, offering clues about how galaxy clusters form and evolve. The cosmic rays emanating from the Cigar galaxy add an almost otherworldly dimension to its character. These high-energy particles, born in the violent aftermath of supernova explosions, travel vast distances, carrying with them the energy of the events that created them. As they interact with the galaxy's magnetic fields and surrounding gas, they leave behind subtle signatures that tell the story of their journey. These interactions produce gamma rays and other high-energy emissions, providing astronomers with a window into processes that would otherwise remain invisible. Recent observations have also revealed unexpected phenomena in the galaxy's outskirts, where faint streams of gas and stars extend far beyond the visible boundaries. These streams, remnants of past tidal encounters, are not merely leftovers, they are active participants in the galaxy's ongoing evolution. They act as reservoirs of material that can be drawn back into the galaxy, fueling future star formation and contributing to the cycle of activity that defines M82. At the same time, these streams connect the galaxy to its environment, highlighting the interconnected nature of the universe. The Cigar galaxy's influence extends even beyond its immediate surroundings, shaping the behavior of the intergalactic medium on a scale far larger than its physical size. The heavy elements it expels through its super wind become part of the cosmic chemical cycle, enriching the gas that permeates the space between galaxies. These elements, essential for the formation of planets and life as we know it, are carried across vast distances, ensuring that the galaxy's legacy endures long after its starburst activity fades. What truly sets the Cigar galaxy apart is its ability to continually surprise and inspire. With every new observation, new questions arise, driving scientists to explore deeper and think more creatively about the universe and its workings. What mechanisms sustain such an intense starburst for so long? How will the galaxy evolve after its supply of gas is exhausted? And what does its story tell us about the fate of other galaxies, including our own? The answers to these questions lie in the data yet to be collected, the theories yet to be tested, and the discoveries yet to be made. As we continue to study this extraordinary galaxy, it reminds us that the universe is far from static. It is a place of constant motion, transformation, and discovery, a boundless frontier where every answer leads to new mysteries, and every observation reveals a deeper truth. The Cigar galaxy stands as a testament to the universe's infinite complexity and beauty. It is not just an object of study, it is a cosmic symphony, a dynamic masterpiece that speaks to the interconnectedness of all things. To explore it is to embark on a journey into the heart of creation itself, a journey that promises to redefine our understanding of the cosmos and our place within it. The Cigar galaxy, with its ceaseless, invites us to imagine the forces that have shaped it into one of the universe's most dramatic spectacles. It is a cosmic paradox, a place where the violent forces of destruction coexist with the nurturing processes of creation, where the fabric of space is constantly torn apart and rewoven by the interplay of gravity, radiation, and time. Each layer of its structure, each glowing filament of its outflows, tells a story that stretches across millions of years, a tale of transformation that continues to unfold before our eyes. The galaxy's superwind, that awe-inspiring plume of gas and dust, is more than just an energetic byproduct of its core, it is a force of cosmic engineering. As this material is flung outward at extraordinary speeds, it sculpts the intergalactic environment, carving paths through the surrounding medium and creating turbulent regions where gas densities fluctuate wildly. These disruptions ripple outward like waves on a cosmic ocean, their echoes reshaping the galaxy's outskirts and even influencing the broader M81 group. The sight of this superwind, radiating in hues of red and gold as ionized gas interacts with the surrounding space, is a vivid reminder of the sheer scale and power of the processes at work. Deeper within the Cigar galaxy lies a crucible of stellar birth unlike anything found in the Milky Way. Here, the interstellar medium is not the quiet nursery of stars but a roaring inferno of activity, where gas and dust are compressed, heated, and blasted apart in a never-ending cycle. Massive molecular clouds, the raw material for star formation, are constantly buffeted by the winds of young stars and the shockwaves of supernovae. These clouds fragment and collapse in unpredictable ways, creating clusters of stars that range from diminutive red dwarfs to gargantuan blue giants. In this chaotic environment, stars live fast and die young. The most massive among them burn through their nuclear fuel in mere millions of years before exploding as supernovae, releasing enormous amounts of energy and scattering the elements forged in their cores. These explosions, though violent, are essential to the galaxy's evolution. They seed the surrounding gas with heavy elements, providing the ingredients necessary for the formation of planets, complex molecules, and, eventually, life. At the same time, the shock waves from these supernovae compress nearby gas clouds, triggering new waves of star formation. This cycle of destruction and creation drives the galaxy's extraordinary starburst activity, sustaining it across cosmic timescales. At the heart of this chaos lies a supermassive black hole, millions of times the mass of the Sun. While not as luminous as the active galactic nuclei found in quasars, this black hole exerts a subtle but profound influence on the galaxy. Its immense gravity shapes the motion of stars and gas in the central regions, while its occasional outbursts of energy, caused by the infall of matter, create ripples that propagate outward. These ripples interact with the surrounding material, adding yet another layer of complexity to the galaxy's already turbulent dynamics. Play of forces within the galaxy is further complicated by the presence of large-scale magnetic fields. These fields, invisible to the human eye but detectable through their influence on charged particles, thread through the galaxy like an unseen skeleton. They guide the flow of gas and dust, influence the formation of stars, and shape the structures of the galactic superwind. Recent studies have revealed that these magnetic fields extend far beyond the visible boundaries of the galaxy, forming bridges that connect M82 to its neighbors. This discovery underscores the interconnected nature of the universe, where even the most distant objects are linked by unseen forces. Beyond the central regions, the Cigar galaxy's halo offers a quieter but no less fascinating view of its ongoing evolution. This diffuse envelope of gas and stars is a repository of history, containing remnants of past interactions, ancient stars ejected from the galaxy's core, and streams of material torn away by gravitational encounters with M81. The halo is also a stage for the interaction between the galaxy and the intergalactic medium, where outflows of gas mix with the surrounding environment, enriching it with the elements needed to form new stars and galaxies. The relationship between M82 and M81 remains one of the most compelling aspects of the Cigar galaxy story. These two galaxies, locked in a gravitational embrace, have influenced each other in profound ways over the course of their shared history. Their interactions have triggered tidal forces that have stretched and warped their structures, ignited bursts of star formation, and created vast streams of gas and stars that weave through the space between them. These encounters are a microcosm of the processes that shape galaxy clusters and groups, offering a window into the larger-scale dynamics of the universe. The Cigar galaxy's influence extends far beyond its immediate surroundings. Its superwind, carrying enriched material into the intergalactic medium, contributes to the cosmic cycle of matter. The heavy elements ejected by M82, carbon, oxygen, iron, and others, become part of the universal inventory, forming the building blocks of future stars, planets, and even life. This process, known as chemical enrichment, is one of the fundamental mechanisms by which the universe evolves, transforming simple hydrogen and helium into the complex array of elements found today. Observing the Cigar galaxy is like witnessing a cosmic symphony, with each component playing its part in a grand, ever-changing composition. From the rapid-fire birth of stars to the slow drift of tidal streams, from the searing heat of the galactic core to the cool expanses of the outer halo, every element contributes to the galaxy's story. It is a story of resilience, transformation, and interconnectedness, a reminder that even in the vastness of space, nothing exists in isolation. As telescopes grow more powerful and our understanding of the universe deepens, the mysteries of the Cigar galaxy will continue to inspire. What secrets still lie hidden within its turbulent heart? How will its story evolve over the next billion years? And what lessons can it teach us about our own galaxy, our place in the cosmos, and the forces that have shaped the universe from its earliest days? These questions drive us to look closer, think bigger, and dream further, as we strive to uncover the truths written in the stars. The Cigar galaxy remains a symbol of cosmic intensity, an endless source of fascination and a reminder of the boundless energy that permeates the universe. Each of its features, from its central chaos to its far-reaching halo, demands further exploration, urging us to dive deeper into its mysteries and marvel at its relentless evolution. It is as though the galaxy itself is alive, its fiery heart beating with the rhythm of creation and destruction, its outflows breathing life into the surrounding cosmos. The super wind, which continues to stretch thousands of light years into intergalactic space, is more than just a dramatic feature. It is a force that connects the galaxy to the wider universe. Like the exhalations of a giant, the winds carry molecular gas, ionized plasma, and heavy elements into the void, where they enrich and transform the intergalactic medium. This process is not merely a local phenomenon. The materials ejected from the galaxy are part of a larger cycle that shapes the evolution of the cosmos itself. In a way, the Cigar galaxy acts as a cosmic alchemist, transmuting raw hydrogen into heavier elements and then scattering these treasures into the universe, where they become the seeds of future worlds. Within the galaxy's turbulent core, star formation continues at a breathtaking pace. The molecular clouds that serve as the nurseries for these stars are immense, chaotic structures, shaped and reshaped by the energy of their surroundings. These clouds are bombarded by ultraviolet radiation, stellar winds, and the shock waves of nearby supernovae, creating a dynamic and often violent environment. Yet, despite this turbulence, these regions manage to produce stars at an extraordinary rate, a testament to the resilience of the processes that govern cosmic creation. The stars born within the Cigar galaxy are not ordinary. Many of them are massive, short-lived giants, burning through their fuel in a few million years before as supernovae. These explosions are not just endpoints, they are beginnings. The shock waves they create compress nearby gas clouds, triggering new waves of star formation. At the same time, the heavy elements forged in their cores are scattered into the surrounding medium, enriching it with the ingredients needed for planets, moons, and even life. The galaxy's central supermassive black hole, though less prominent than those in active galactic nuclei, plays a quiet yet profound role in this cosmic theater. Its immense gravity influences the motion of stars and gas in its vicinity, while occasional infalls of matter onto its event horizon produce bursts of energy that ripple through the surrounding space. These interactions add another layer of complexity to the galaxy's core, where gravity, radiation, and turbulence combine to create an environment unlike any other. The magnetic fields threading through the galaxy are another key player in this cosmic symphony. Invisible to the eye, these fields shape the flow of gas and dust, channeling the galaxy's energy and influencing the formation of its superwind. Recent studies have revealed that these fields extend far beyond the galaxy's visible edges, forming structures that connect M82 to its environment and beyond. These discoveries highlight the unseen forces that bind the universe together, revealing a hidden architecture that shapes the behavior of galaxies on the largest scales. The tidal interactions between the Cigar galaxy and its neighbor, M81, continue to leave their mark on both systems. These encounters, which began millions of years ago, have triggered waves of star formation, created streams of gas and stars, and reshaped the structure of both galaxies. For the Cigar galaxy, these interactions have been a driving force behind its starburst activity, compressing its gas and igniting the rapid formation of new stars. For M81, they have created tidal tails and bridges, visible evidence of the gravitational dance that has bound these two galaxies together. The halo surrounding the Cigar galaxy is a quiet yet profound reminder of its cosmic influence. This diffuse region, extending far beyond the galaxy's disk, contains a mixture of ancient stars, expelled gas, and remnants of past interactions. It is a place where the galaxy's history is written in streams of stars and filaments of gas, each one a record of an encounter, an event, or a transformation. The halo also serves as a gateway between the galaxy and the intergalactic medium, where the materials ejected by the superwind mix with the surrounding environment, enriching it with the elements of life. Cosmic rays, high-energy particles born in the aftermath of supernova explosions, add yet another layer of intrigue to the Cigar galaxy. These particles, traveling at nearly the speed of light, interact with the magnetic fields and gas in and around the galaxy, producing gamma rays and other high-energy emissions. These interactions provide astronomers with a unique window into the most energetic processes in the galaxy, revealing the hidden dynamics of its core and outflows. As we continue to observe and study the Cigar galaxy, we are reminded of its role as a microcosm of the universe itself. Its starburst activity mirrors the processes that occurred in the earliest galaxies, giving us a glimpse into the conditions that prevailed in the young universe. Its interactions with M81 and the larger M81 group reflect the dynamics of galaxy clusters and the forces that shape the cosmic web. Its superwind and halo illustrate the interconnectedness of galaxies, showing how each system contributes to the larger story of the universe. The Cigar galaxy is not just a distant object to be observed, it is a source of inspiration, a reminder of the power and beauty of the cosmos. It challenges us to think beyond our own world, to imagine the forces that shape galaxies and stars, and to ponder the vastness of the universe and our place within it. With every new observation, every discovery, we come closer to understanding the intricacies of this extraordinary galaxy and the countless others like it that fill the cosmos. Yet, even as we uncover its secrets, the Cigar galaxy continues to surprise us. Its ever-changing nature, a testament to the boundless complexity of the universe. The Cigar galaxy, ever enigmatic and brimming with cosmic vitality, remains a marvel that defies simplicity and rewards relentless curiosity. Every corner of its vast expanse pulses with the energy of countless interactions, stellar births and deaths, gravitational dances, and the ceaseless movement of material through space. It stands as a living testament to the raw, untamed forces that shape galaxies, forging order from chaos and scattering beauty across the universe. The galactic superwind, already an iconic feature, grows in complexity the closer it is examined. Stretching tens of thousands of light years from the galaxy's core, this colossal outflow is more than a mechanism of expulsion. It is a dynamic engine of transformation. As the ejected gas cools and interacts with surrounding matter, it forms intricate filaments and bubbles, glowing faintly as they drift through the intergalactic medium. These structures, captured in incredible detail by advanced telescopes, seem almost alive, shifting and reshaping under the influence of turbulence, radiation, and magnetic fields. Within them, new processes begin fold. The cooling gas begins to condense, forming dense clumps that may one day coalesce into new stars or even seed the formation of smaller satellite galaxies. The central regions of the galaxy are a realm of extremes. Here, dense molecular clouds serve as the breeding grounds for stars, their chaotic interiors illuminated by the searing radiation of young, massive stars. These stellar nurseries are turbulent, filled with swirling gas and dust that is sculpted by the immense energy pouring out from the stars they produce. The pressure in these regions is thousands of times greater than that in typical galaxies, creating a crucible where the rules of star formation are pushed to their limits. The stars that emerge from this chaos are born into an environment that is as hostile as it is fertile, where their lives are measured in millions of years, mere moments on cosmic time scales. The most massive stars, those destined to end their lives as supernovae, play a pivotal role in the galaxy's evolution. Their explosive deaths not only release tremendous amounts of energy, but also send shockwaves rippling through the surrounding medium. These shock waves compress nearby gas clouds, triggering yet another wave of star formation. This feedback loop, where destruction leads to creation, is one of the defining characteristics of the Cigar galaxy. It ensures that the galaxy's starburst activity continues, even as it depletes the very material that sustains it. Amidst this frenzy of activity, the supermassive black hole at the galaxy's center sits as a quiet yet powerful force. Its gravitational pull shapes the orbits of stars and gas in the central regions, creating a dense, rotating disk that feeds material toward the black hole. Occasionally, as gas and dust spiral inward, they are heated to millions of degrees, emitting bursts of energy that light up the galaxy's core. These emissions, though brief, ripple outward, influencing the behavior of the surrounding gas and adding yet another layer of complexity to the galaxy's inner dynamics. The magnetic fields threading through the galaxy act as invisible architects, shaping the flow of matter and energy. Recent studies have shown that these fields are not uniform, but instead form complex, layered structures that extend far beyond the galaxy's visible disk. These magnetic fields interact with the charged particles in the galaxy's superwind, creating patterns of motion that are both chaotic and ordered. They also play a role in the acceleration of cosmic rays, guiding these high-energy particles as they travel through the galaxy and beyond. The halo of the galaxy, often overlooked in favor of its more dramatic features, is a region of quiet significance. This diffuse envelope of gas and stars tells the story of the galaxy's past interactions, its material shaped and reshaped by the gravitational pull of neighboring galaxies. Streams of stars and gas, remnants of tidal encounters with M81, crisscross the halo, forming faint structures that stretch far into space. These streams are not static. They move and evolve, gradually blending into the intergalactic medium. The halo is also enriched by the material expelled in the superwind, which mixes with the older stars and gas to create a region of stunning complexity. The tidal interactions between the Cigar galaxy and M81 continue to captivate astronomers. These encounters, which have occurred over millions of years, have left indelible marks on both galaxies. For M82, the gravitational forces exerted exerted by its larger neighbor have stirred up its gas and dust, triggering waves of star formation and reshaping its structure. For M81, the encounters have created long tidal tails and bridges, forming intricate patterns that connect the two galaxies. These interactions are not merely a local phenomenon. They are a microcosm of the processes that shape galaxy clusters and the cosmic web. The influence of the Cigar galaxy extends far beyond its immediate surroundings. Its super wind, carrying in rich material into the intergalactic medium, contributes to the broader process of cosmic evolution. The heavy elements it expels, carbon, oxygen, iron, and others, become part of the universal inventory, the building blocks of future stars, planets, and even life itself. This cycle of enrichment, where galaxies like M82 seed the universe with the elements of complexity, is one of the most profound processes in the cosmos. Every new observation of the Cigar galaxy reveals additional layers of complexity, challenging our understanding of how galaxies form, evolve, and interact. From its fiery core to its windswept halo, from its dense star-forming regions to its quiet tidal streams, every aspect of this galaxy speaks to the interconnected nature of the universe. It reminds us that even the most distant galaxies are part of a larger whole. Their actions shaping the cosmos in ways we are only beginning to understand. As we continue to study this remarkable system, the Cigar galaxy becomes not just an object of scientific inquiry, but also a source of inspiration. Its relentless energy, its capacity for renewal, and its role in the grander cosmic narrative remind us of the boundless possibilities that the universe holds. It is a beacon of discovery, a reminder that even amidst the chaos of creation, there is beauty, purpose, and an unending story waiting to be told. The Cigar galaxy, like an eternal flame burning in the darkness of space, refuses to be silent or still. Its very existence is a declaration of the universe's creative and destructive powers, a place where matter collides, transforms, and reshapes itself on scales that defy human comprehension. It is a galaxy alive with activity, a cosmic forge where stars, elements, and entire structures are born and reformed in a never-ending cycle of cosmic alchemy. The galaxy's superwind continues to astonish astronomers with its complexity and sheer power. It is not a uniform stream of expelled matter, but a dynamic, ever-changing phenomenon filled with turbulence and structure. Within this superwind, vast streams of ionized gas swirl like ribbons of fire, glowing in vivid red and orange hues as hydrogen atoms are excited by intense radiation. Embedded within these flows are dense knots of material, regions where gas is cooling and condensing, potentially setting the stage for the formation of small satellite systems or isolated stars far from the galaxy's core. These pockets of future potential carry the essence of M82's legacy, seeding the vast intergalactic medium with the tools for creation long after the galaxy itself has quieted. At the heart of this superwind lies the galaxy's starburst core, a region of unrivaled energy in chaos. Packed within a relatively small area, countless massive stars live out their short but brilliant lives, their combined light illuminating the entire galaxy. The gravitational interplay within this core is extraordinary, as massive molecular clouds collapse under their own weight while being simultaneously ripped apart by the immense forces around them. Here, in this maelstrom of gravity, radiation, and turbulence, stars are forged at a rate that dwarfs the star formation activity of calmer galaxies like the Milky way. Supernovae occur frequently in this region. Their explosive power reshaping the interstellar medium with each burst. These titanic explosions release energy equivalent to the total output of the Sun over billions of years, creating shockwaves that ripple through the dense gas clouds. The shockwaves compress the gas, triggering further star formation, even as they disperse and enrich the surrounding medium with elements forged in the dying star's cores. This relentless feedback cycle ensures that the starburst activity remains sustained, making the Cigar galaxy one of the most prolific star factories in the universe. The Cigar galaxy, also known as M82 or Messier 82, is one of the most fascinating objects in the observable universe. It lies in the constellation Ursa Major, and is approximately 12 million light-years away from Earth. This peculiar galaxy has captured the attention of astronomers and astrophysicists due to its intense starburst activity, unique structural features, and dynamic relationship with its cosmic neighbors. M82 is classified as a starburst galaxy, a type of galaxy experiencing an extraordinary rate of star formation. The rate of star production in this system is about 10 times higher than in our Milky Way, with an estimated new star forming every year. This rapid birth of stars is fueled by an abundance of interstellar gas and dust, which collapse under gravity to form stellar nurseries. However, the conditions within the Stokes galaxy are far from tranquil. The immense energy released during star formation creates powerful stellar winds and supernova explosions that disrupt the surrounding interstellar medium. This turbulent environment is a hallmark of starburst activity. One of the most striking features of the Cigar Nebula is the vast, fiery outflow of gas and dust streaming outward from its central regions. This phenomenon, known as a galactic superwind, is driven by the collective energy of thousands of massive, young stars and supernovae. The superwind is composed of ionized hydrogen, oxygen, and other elements, which are ejected into the intergalactic medium at speeds exceeding 1,000 kilometers per second. These outflows are not only visually spectacular, but also play a crucial role in the evolution of the galaxy. By expelling gas and dust, the superwind limits future star formation within the system and enriches the surrounding intergalactic environment with heavy elements. The starlight forge has a highly irregular and distorted shape, making it an atypical member of the galactic family. Its elongated structure and chaotic morphology are likely the result of gravitational interactions with its neighboring galaxy, M81. The two galaxies are part of the M81 group, a small collection of galaxies bound together by gravity. Over the past few 100 million years, the gravitational forces between M82 and M81 have triggered tidal interactions that have stirred up the gas and stars within both systems. These interactions are thought to have initiated the intense starburst activity within the torch galaxy. A distinctive feature of the smoldering spiral is its central region, where a supermassive black hole resides. This black hole, millions of times the mass of the Sun, influences the dynamics of the galaxy's core. Observations in multiple wavelengths, including X-rays, radio, and infrared, have revealed the presence of an active galactic nucleus, AGN, at the heart of the galaxy. The AGN emits high-energy radiation, which interacts with the surrounding matter and contributes to the overall energy output of the system. This interaction is another factor driving the extreme conditions within the Ember galaxy. In addition to its superwind and starburst activity, the glowing inferno is notable for its complex magnetic field. Studies using polarized radio observations have revealed large-scale magnetic structures extending outward from the galaxy's central regions. These magnetic fields are believed play a role in shaping the galactic superwind and influencing the distribution of cosmic rays. Understanding the interplay between magnetic fields and galactic dynamics is a key area of research in modern astrophysics, and the flame nebula provides an excellent laboratory for studying these phenomena. The radiant rift is also a prolific source of cosmic rays and high-energy particles. Observations in gamma rays and X-rays have shown that the galaxy's core is teeming with energetic phenomena. These emissions are associated with the intense star formation and supernova activity occurring within the system. Cosmic rays generated in the galaxy's core propagate outward, interacting with the interstellar medium and contributing to the overall energy budget of the surrounding space. One of the most significant discoveries about the bright beacon came from observations in the infrared spectrum. Using advanced space-based telescopes such as the Spitzer Space Telescope and the Hubble Space Telescope, astronomers have mapped the distribution of dust and molecular gas within the galaxy. These studies have revealed a complex network of filaments and clumps where star formation is occurring at an extraordinary rate. Infrared observations have also provided insights into the temperature, composition, and dynamics of the interstellar medium, shedding light on the processes driving the galaxy's starburst activity. The starfire expanse is not just a spectacle of astrophysical phenomena, but also a key player in the cosmic ecosystem. The materials ejected in its superwind, including heavy elements like carbon, oxygen, and iron, enrich the intergalactic medium and contribute to the chemical evolution of the universe. These elements are the building blocks of planets other galaxies, making the galaxy's activity a crucial part of the cosmic cycle. In recent years, the beacon of creation has been the focus of numerous studies using advanced observatories and instruments. Telescopes like the Chandra X-ray Observatory, the Very Large Array, and the James Webb Space Telescope have provided high-resolution data across multiple wavelengths, allowing researchers to study the galaxy in unprecedented detail. These observations have not only deepened our understanding of the galaxy itself, but also provided valuable insights into the broader processes of galaxy evolution, star formation, and cosmic feedback. Despite its relative proximity to Earth, the Cigar galaxy continues to hold many mysteries. Questions remain about the exact mechanisms driving its starburst activity, the long-term effects of its interactions with M81, and the fate of its expelled gas and dust. As observational technology continues to advance, astronomers are likely to uncover even more secrets about this dynamic and enigmatic system. The Torch Nebula serves as a vivid reminder of the dynamic and interconnected nature of the universe. Its intense activity, dramatic outflows, and complex interactions with its environment exemplify the forces that shape galaxies and influence their evolution over cosmic timescales. For scientists and enthusiasts alike, the Stoga spiral remains a source of wonder and inspiration, a celestial beacon illuminating the complexities of the cosmos. The Cigar galaxy, or Messier 82, remains a prime focus of astronomical studies not only for its unique features, but also for the critical role it plays in unraveling the mysteries of galaxy evolution. This starburst system is a living laboratory, showcasing the dynamic interplay between gravity, star formation, and cosmic feedback on an extraordinary scale. of the lesser discussed, but equally fascinating aspects of the fiery veil is the role of supernovae in shaping its environment. Supernova explosions, the catastrophic deaths of massive stars, release immense amounts of energy and enrich the surrounding interstellar medium with heavy elements. These events also drive shockwaves through the galaxy, compressing gas clouds and triggering further waves of star formation. In the case of M82, the supernova rate is significantly higher than that of typical galaxies, with a new supernova occurring approximately every 20 to 30 years. This elevated rate underscores the intensity of the starburst activity and its profound impact on the galaxy's overall structure and evolution.